to these are just achievement indicators. They're basically like your curriculum. So these ones here, on your diploma you have this thing called puzzles and games. It's like a section. The first 2 to 3 questions on the diploma are them. It could be like Sudoku, it could be like solving ones where it's like 3 people work in the world, and one of them is a teacher, and one of them is a doctor, and one of them is a lawyer. The teacher lives in the land that is the longest name, and the doctor lives in the place with the shortest name, and then you have to like logic puzzle around them, things like that. So we're going to practice just logic puzzles throughout, but we're not going to do like a unit on logic puzzles because that's just not a thing. But these are the achievement indicators. So I can determine, explain, and verify strategy to solve a puzzle or to win a game. I can identify and correct errors in a solution to a puzzle or in a strategy, because sometimes they'll give it and then they'll say fix the errors in the puzzle of it. And then I can create a variation on a puzzle or a game and describe a strategy for solving the puzzle or winning the game. So those are the things that we're going to talk about after as we go along, and then you can give yourself a score from 0 to 5. Hopefully by the end you're 5 on the whole thing. This is the unit that we're on. It's set theory. So we're going to be able to, I can provide examples of an empty set, disjoint set, subsets, universal sets in context, and explain the reasoning. I can organize information such as collected data and number properties using graphic organizers, explain the reasoning. So we're going to go through all of these, and at the end we're going to come back to this front page and make sure we can have 5s across the board of what we can do. Okay? As of right now, I would say most people would be at 0s on all of these, and you should be. You haven't learned it. It's brand new. Right? So the first page is this. We're going to go through some definitions. So today's a heavy definition day, but it's not like the whole course is definition. It's just today's a heavy definition day. So the natural numbers. You guys talked about all these number sets in grade 10. They were talked about a lot in grade 10. You've talked about the other sets before grade 10, but in grade 10 we talked a ton about these sets. So the natural numbers are like the ones that you naturally count. That's what I would say. Like when you can walk up to a toddler, the toddler's not like -3, -2, no toddler's naturally counting negatives. No toddler naturally goes 0, 1, 2. Like toddlers don't start at 0. What do you naturally start counting when you start counting? 1, 2, 3, 4, etc. Right? That's the natural numbers, the ones you naturally count. My board just does what it wants, just so you know, in case you were wondering. It's really super. So those are the natural numbers. We talk about them in grade 10 a lot. We talk about all of these. Then comes the whole numbers in the world. So you naturally realize in the world there's 1, 2, 3, 4, 5, etc. Right? Then you realize there's whole numbers, which is literally the natural numbers plus the number with a whole. That's it. What's the number with a whole? Yeah, 0. That's it. It's 0 and the natural numbers. That's all the whole numbers are. So the whole numbers are actually, the natural numbers are a subset of the whole numbers, because the natural numbers are completely contained in the whole numbers. So the whole numbers are 0, 1, 2, 3, 4, etc. So it's the natural numbers plus the number with the whole, which is 0. So the natural numbers are a subset of the whole numbers, which means all of the natural numbers are contained in the whole numbers. Okay? Then we get to like grade 7. And then they tell us there's these negative numbers in the world. And your life gets a lot more rough in so many ways. There's these things called the integers. What are the integers? Does anyone remember? Like -3, -5, -8, -2. But also 1, 7, 8, and also 0. So the integers are the natural numbers, the whole numbers, plus the negative numbers. That's all the integers are. So the natural numbers and the whole numbers are a subset of the integers as well. So the integers are like -3, -2, -1, and then the whole numbers, and then the natural numbers, but not decimals. And then we have the rational numbers. So the rational numbers are the ones that are a little crazy, but they can be rationalized. Rationalized means turned into a fraction. Okay? So anything that can be turned into a fraction is a rational number. We'll talk about which ones they are. Can be converted to a fraction. So instead of converting to a fraction, let's look at fractions turned into decimals and see what we get. Okay? So one example could be, if we're going from a, see, I told you my board does what it wants. Like what was, say I use 3/4. Does anyone know what 3/4 is as a decimal? Yeah. Exactly. So 3/4 is a rational number, but also is 0.75. That's rational too. What if we look at another fraction? What if we look at 1/3? Does anyone know what that is as a decimal? Yeah. Yeah. 0.333. The way they used to write it is they would write it as 0.3 with a dot. If it's more than one number repeating, it's a bar. Remember how they used to do that? So not only is 1/3 rational, 0.333 is rational. So what kind of decimals can be converted to fractions? If I work backwards now, instead of a fraction to a decimal, decimals to fractions. What specific types of decimals can be converted to fractions? What kind of decimal is this? Starts with an R. Rhymes with repeating. Come on, you know it. I believe in you. Thanks. You said repeating? Good job. Yeah, totally. Totally. Cool, cool, cool. So repeating decimals are rational. So it could be like 0.67676767. That's still a repeating decimal, right? What kind of decimal is this? Starts with a T. Someone said it in a whisper answer. Yeah.
Is it terminating?
Yes. You got it. Marcus rocks. So terminating decimals. So repeating decimals and terminating decimals can all be made into fractions, therefore they are rationals. Also, rational numbers include every other subset between that. Like, because any of the numbers previous to this, integers, whole numbers, naturals, these can also be converted to fractions, can they not? Every number can be written over what number? 1. Every single number can be written over one number, over the number 1, sorry. So therefore, those would be converted to fractions as well, right? So not only is it repeating and terminating decimals, it's also integers, which contain whole numbers and naturals. All of those are rationals because they can be converted to decimals. So if rationals contain integers, wholes, naturals, terminating decimals, repeating decimals, what's the only thing left for irrational numbers? Not whole numbers, not natural numbers, not integers, not repeating digits, or not repeating decimals, not terminating decimals. What's left? Non-repeating and non-terminating decimals. I'm gonna crack you guys. You're gonna answer so many questions within a week. You're gonna be like, I'm gonna be like, guys, chill. Don't answer so much. That's what's gonna happen. I feel it. Non-repeating, non-terminating. What's the most common one that's a non-terminating, non-repeating? number? Yeah. Pi. Pi is the most known irrational number. Because it doesn't repeat and it doesn't terminate. It's 3.14159 and it blah, 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 blah. Keeps going, right? So pi is the most well-known irrational number. We're also going to look at another one this year that is e. It's used with logs. You can do e to any power. Most often it's e to the 1, but you don't usually write 1. It's 2.7181 and it keeps going and it doesn't repeat. So that's going to be another common one that you'll know at the end of 30-2. Now the real number system actually encompasses everything but non-real numbers. So non-real numbers would be like the square root of a negative number, because you can't take the square root of a negative, right? It would get you an imaginary. So reals actually cover all this stuff. They cover the naturals. They cover the wholes. The integers. The rationals. And the irrationals. And we want to talk, we're going to get to subsets, but I want to explain subsets a little bit before that. So in grade 10, they would always draw a diagram like this. It would be a box, and then this would be the real number system. This would be the entire box. And then this box would be split into rationals, and irrationals. And then in the rationals, we had integers. And in the integers encompass the whole numbers. And in the wholes, we had the naturals. So like the naturals were engulfed in the wholes were engulfed in the integers were engulfed in the rationals were engulfed in the reals, right? Because natural numbers are 1, 2, 3, 4, 5, 6. Wholes are all those numbers plus the 0. Irrationals are all those numbers plus the negatives, etc., or integers, etc., etc. So what we can actually say, because every natural number is a whole number, correct? Every natural number is a whole number. Natural numbers 1, 2, 3, 4. Whole numbers 0, 1, 2, 3, 4. We can actually say that the natural numbers are a subset. It's this long sideways C. And you're going to get this formula sheet. I just printed you off because I got extra people. But the subset is this symbol here. This is your actual formula sheet for 30-2. It's not this big, though. That would be kind of weird to have that in your diploma this large. But it looks exactly, that was funny. No one laughed. Cool. Subset is like a longer sideways, can't speak, sideways C. And it's a subset. So N would be a subset of the whole numbers. This just means subsets. And that just means everything in N, all the natural numbers, are in the whole numbers, right? Is there anything else we could say is a subset of something? Any other letters, do you think? I believe in it. Yeah.
Whole numbers are subset of the integers.
You get one of these two. Good job. The whole numbers are a subset of the integers. So true. Because every whole number is an integer. You're right. Because every whole number is an integer. The whole numbers are 0, 1, 2, 3, 4, 5, 6 onwards. The integers are all of those plus negatives. So in order for something to be a subset, all of this has to be in this. Every single one that's in here has to be in here. Oh, prime numbers. Anyone remember what the definition of a prime number is? Anyone know? Anyone know? I'm singing it. Anyone? Period 4 is the best. This room is really hot, and no one's answering me. Yeah, exactly right. You totally true. Yes, prime numbers have two factors, one in themselves. Good answer. No one answered me. No one did. That was me answering. That was me trying. Cool. Prime numbers have two factors. One and itself. That's it. One and itself. It has to have two factors, two different factors maximum. So prime numbers have two different and only two different. Sometimes they use the word in math distinct, because that means the same word is different. Factors. The number 1 and itself. So an example could be like 5. Factors, two numbers that multiply to get that number, right? So 5, you multiply 1 and 5. That's it. 2 factors. 11, 1 and 11. 29, 1 and 29. What about 24? 1 and 24. 2 and 12. 3 and 8. 6 and 4. There's a whole bunch. That's not prime, correct? What about the number 1? How many factors does the number 1 have? Just 1. It's literally just the number 1. So the number 1 is super different. It doesn't fit in prime, and it doesn't fit in composite. It is neither. It's neither prime nor composite. The number 1 is always, for the longest time, you guys will write the number 1 as prime. It is not. Because prime has to have 2 factors. Only 2 factors. No more than 2 factors, no less than 2 factors. 2 factors. So the number 1 is not prime. I'm going to write this down here so that when the test comes and you guys tell me the number 1 is prime, you're wrong, and then I'll bring you back to this spot. So number 1 is not prime nor composite. $16.53 on the podcast. I will bring you back to that point if you write the number 1 as prime. 16.53. Got it down. Rewind that baby back. Here we go. What is the first prime number? Rhymes with Sue. Yes, it's 2. I had a different word. I didn't want to say it. I couldn't get past the word poo. It was what was. I just said it. Anyways, didn't mean to. So anyways, yes, the first prime number is 2. It is also the only what prime number? Yes, you guys are answering more. Thank you. Good job. Okay, it is the only even. So our examples of prime are the number 2, it's the smallest and the only even. Now 4 is no longer prime. 4 will be your next even, and it can't be prime because it has the factors 1, 4, and 2. That's 3 factors, right? It's out the window. 6, 1, 6, 2, 3, right? Anything greater than 2 is going to have 2 as one of its factors. So you're going to always get more than 2 factors, right? So 2 is the only even prime. What's our next prime? You guys are doing so well. Just shout it out. I believe in you. Come on. Oh my gosh. Stopping there. It's 3. Thank you. Woo. 3. Then what? You just keep going. You're on a roll. Come on. 5. Yes. Believe in yourself.
11.
Yeah.
That's what I'm counting out.
No, you got it. It's a bad number. No one likes it.
13.
Yes. Not 14, not 15, not 16, but? See, we can work as a team. Not 18, but?
19.
Uh-huh. Not 20, not 21, not 22, but? See, look at you. So good. And I keep going. Because their only factors are 1 in the number. Yes? Okay. Composites have what factors? Oh, more than, oh no, I wasn't looking for a hand. That's great. No, not 2 or more. More than 2. Yes. Because 2 would hit us into primes. So more than 2. Exactly right. So composite numbers have more than 2 factors. So what's our first composite? It is not 1. Please do not give me 1 as your answer. Yes. 4. You already got a heart. I can't give you 2. That would just, everyone else be so jealous. I get it. If you guys answered, you get, oh, sorry, I didn't give you one. That was rude. Oh, and, okay. 4, then what? Rhymes with sticks. Oh gosh, 6. It's not there. 8, 9, 10, 12, 14, 15, 16. You get the point. So are prime numbers and composites opposite? Trick question. Are prime and composites opposite? Almost opposite. What do they both not have in common? What do they both not have? What number? 1. So we call things that are opposites complements in math. We'd say that, like, we can't say that primes and composites are actually complements of each other. We can't say they're opposites because the number 1 doesn't fit in either of them, right? Are odds and evens complements? Odds and evens? Are they complements? Yeah. What's not odd is even, what's not even is odd. So those are complements. But primes and composite numbers aren't, just because they both don't contain 1. Okay? Multiples of 3. I know this is taught in grade 7 at the very least. I think it's taught earlier, because no, it has to be taught in like grade 5. Because my daughter had it, I think, last year. Multiples of 3. Starts with the number 3, goes up by? Yes. I don't think I gave you one. Did I give you one already? I think that's 2. I think now you're going to be jealous. Sorry. Okay, so just throwing them out there. It's fine. So 3, then? Yeah, then? Doing so good. I was like, and then? Yep, and then? And then? Someone's answering me. I'm just going to keep going. Yeah, uh-huh. Okay. I was having so much fun. Didn't have to pull answers out of people. Okay, factors of 12. I don't know what put an equal sign. That's not real. Example. Factors of 12. 1 and? Rhymes with 12. Oh, wait, it is 12. Cool. Thanks. 12, then? 2 and? Yeah, and then? And? Voila. And because there are 6 factors of 12, it is a what number? Yes. I didn't even have to, I just stared at you, and then you answered it. It was so great. Cool. Yes. Okay. Divisible by 5. What numbers are divisible? What does divisible by mean? Anyone? If I divide it, I don't get a what? Decimal. I don't get a remainder. Don't get a decimal. Exactly. So what is divisible by 5? What's the first one? 5. This is getting so much better. 5, then? Yeah, it's almost like multiples, right? Very similar. Very good. Then we're going to flip over. So many words, so little time. All right. In mathematics, a set can be defined as a collection of distinct objects. For example, the number of faces of a die, and if they use them, it's a 6-sided die, form a set. Sets are usually denoted by capital letters or by descriptions in curly brackets. An object in a set is referred to as an element. The number 5 is an element of the sets of numbers of a die. So, for example, if we were looking at a 6-sided die, if we wanted to list the elements of this set, and the set being set A, right? We would say capital A, so set A equals, and then we use these squiggly brackets. The squiggly brackets, and you've used them in domain and range for forever, they mean the set of, right? Whenever you do the squiggly brackets, you're saying the set of, then X, such that, X is the noun of the reals. We did that in domain all the time. So the squiggly brackets just mean the set of. So in the set A, we have the elements 1, 2, 3, 4, 5, 6. And that's when we write it out. You could write it as the natural number is less than 7 because the natural numbers start at 1. Or you could say x such that x is less than 7, x and L are the naturals. Most often it's written like this. We just list what's in it. Okay? And the elements of a 6-sided dice are 1, 2, 3, 4, 5, 6. Right? What are the elements on a coin? There's 2 of them. And what are they? On a coin? Heads and tails. So I would use squiggly brackets and I write heads, comma, tails. That's it. Okay? This stuff we know already. The curly brackets together is read the set of. So if you see these curly brackets, they mean the set of. That's been taught to you years and years and years. When you see the squiggly brackets, it means the set of. The straight up and down line, like this one here, it's read as such that. And then E, this little E thing, represents is a member of or is an element of. Now here we have the number of sets in set A is written as N of A. So on a diploma, they could write this N of A. This means the number of elements in. Or most often they'll just literally say this, the number of elements in set A. They'll just literally write the words. Now, if we go N of A, if we go A equals 1, 2, 3, 4, 5, 6. Those were the actual elements, correct? Whereas little n of A means how many there are. So how many elements are there? There's 6. So that's why we put the 6. Now, why would they do that? Why would they ever ask for the number of elements in instead of just asking what the elements are? What special type of question on a test would this feed better into? Multiple choice, we could just do normal, right? Multiple choice can have the answer 1, 2, 3, 4, 5, 6 in squiggly bracket, right? What questions can't have 1, 2, 3, 4, 5, 6 as an answer? Yeah, someone said it. Numeric response. Numeric response can't have, a numeric response is 4 boxes, right? So if you have more than 4 elements, they have to ask for the number of elements in it. They can't actually ask for the elements so that it fits in a numeric response box. Do you know what I mean? So in this case, if they asked you for the answer to this question and it was a numeric response, they'd have to ask for the number of elements in, and your answer would be 6, because there's not 6 boxes. So here it says, note that the number 2 belongs to set A, but the number 8 does not belong to set A. So the way they can express it is 2 is an element of set A. And we know this is set A because it's a capital letter. And then this would be 8 is not an element of set A. The order of listing the elements in a set does not matter. So I listed it 1, 2, 3, 4, 5, 6. I could list it 6, 1, 2, 3, 5, 4. I could list it out of order. Listing it out of order is a chance you're going to miss a number here or there, right? That's the only difference. All right. So we're going to look here. I want you, so it says consider the following 2 sets. P are the whole numbers less than or equal to 3. Q are the even whole numbers less than 10. So I want you to list me the elements in P. And I want you to list me the elements in Q. Right? Like that. I want you to list them. So here it's for A. You're going to put it in here. What is the elements? We're doing this. List the elements in each set. So I want you to tell me what the numbers are that would fall in there. Try it out. If P are the whole numbers less than or equal to 3, what's the first number we're starting at? 0, because it's the whole numbers, right? And then it says less than or equal to 3. Do I put 3 or not put 3? Put 3, because it says less than, but equal to. So 0, 1, 2, and 3. And we need the squiggly brackets, right? Now, how many elements is that? 4. So N of P would be 4. So this could be asked either way in a numeric response, right? Okay. And then Q are even whole numbers less than 10. So we're going to start at 0, 2, 3, not 2, 3, come on, left. 0, 2, 4, 6, 8. Do I put 10? Why not? It says less than 10. It doesn't say equal to. How many of them are there? 5. Okay, then next page. Okay, so here it says, Betty is defining sets using non-negative single-digit numbers. Non-negative meaning, can't be negative. Single-digit means I stop at what number? 9. So I can go 0 to 9, right? From the list of non-negative single-digit numbers, she defines the following as even sets, whole numbers less than 7, odd numbers less than 7. And then I want you to list the elements of each set in the space above. Try it out. I want the elements that would fit in here for each of these. And remember to close your elements off with another one to say the subset. Or not the subset, the set of. So when we're looking at this, we can also talk about a universal set. The universal set are the only, it's going to here. Within the context of any problem in set theory, there generally is some largest set that we have in mind. We refer to this as the universal set. So the universal set are all the numbers that we can even look at. In this case, what are the only numbers we're allowed to even look at? Yeah. The first one even, next one whole numbers less than 7, next one odd numbers less than 7. What's the biggest amount of numbers we're allowed to choose from though? Non-negative single digit, right? That's the only place. So 10 I can't choose from, correct? -1 I can't choose from. So the universal set in this case, universal set is written like this. So U with the bracket like that. Little horseshoes on the top. And the reason why you need the horseshoes on the top is U without them is called union. So it needs to have little things on top. So the universal set of this case would be, what do I start at? What number? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those would be my universal set because that's the only numbers I can pick from to get E, L, and O. Correct? Now E are the evens. So those are subsets. Those are smaller sets. So the evens out of here would be, we're going to include 0, 2, 4, 6, 8. I suspect on a diploma, they'll either say 0 is even, so that you aren't guessing. They'll put it as like a little asterisk below. Or they'll do the natural numbers and just completely bypass putting a 0 in, so then you don't have to figure out if it's even or not. But we're going to include it as an even. But I have seen where they put an asterisk in the box and it's like 0, let 0 be an even number or something like that. Okay? So you're not guessing. Whole numbers less than 7, we go from 0 to what? Where am I going to stop at? 6. Odd numbers less than 7. All right. Odd numbers less than 7. 1, 3, 5. All right. We're going to use these numbers to explain some stuff along the way. So here it says state the universal set for the example above. We did that. We just did it above it. We've talked about subsets. Now we're going to really sell subsets. A subset of a set is a set that contains some or all or possibly none of the elements from a previously defined set. It's totally clear. Like that sentence is perfection, right? Right? All sets we deal with in a problem must be subsets of the universal set, and every set is a subset of itself. Right? This is how I felt in first year university when they were doing proofs, and I was like, girl, please, I don't know what is going on. I have to go home and like reread my notes. I was just lost soul. All right. Don't even know how I got on that sidetrack. Okay, subset. Oh, back again. Thank you. Yeah, this is confusing, the way it's worded. A subset literally is just that when you use a letter, the subset symbol in another letter. So let's say, not these ones. We'll just say A is a subset of B. Let's pretend this. We're just using a totally side different note. All it means is that everything in A has to have the same elements in B. So an example would be if A had 1, 2 in its elements, B would have to have at least what? 1, 2. Could it have more? Sure, but it has to have at least 1, 2. That's it. That's this fancy paragraph of garbage. That's all it means. 1, 2, and smiley face. Poof. A is a subset of B. Could B just have 1, 2? Yeah. Would A still be a subset of B if B was just 1, 2? Yeah. At minimum, B has to have what A has. It could have more, but at minimum, it has to have that. Make sense? Okay. So after we're done that horrific paragraph and my sidetracking, we're back. In set notation, the symbol, this longer U, sideways U, long C, is used to represent the relationship between sets. For example, set E is a subset of the universal set. Is that true? Set E has 0, 2, 4, 6, 8. The universal set has 0, 2, 4, 6, 8, and more. So is it true? Yeah. In order for something to be a subset of it, you just check, make sure all of those are in there, and if there's more, yay. If there's not, it doesn't matter, right? So, E is a subset of U. This is a true statement, since all the elements in E are also in set U. The second bullet says, is set E a subset of set L? Well, let's check it out. E was 0, 2, 4, 6, was there more? I don't remember. 8. And L had what in it? Is it 1, 0? 0 to 6? Okay. Is E a subset of L? So is E a subset of L? Well, let's check it out. Okay, E has 0, L has 0. E has 2, L has 2. E has 4, L has 4. E has 6, L has 6. E has 8, L does not. So is it? No. Everything in this has to be in this. Because this is not, it's done. Right? Does that make sense? Everything in E, all the numbers in E have to be found in L. And if they're not, even if one of them isn't, it's not a subset. You tell me if this is true. Fun times. Okay. Is set O a subset of L? I had a whole bunch of no's. I agree. I do not agree. Why are people saying no? O, a subset of L. O has 1. L has 1. O has 3. L has 3. O has 5. L has 5. Is O a subset of L? Yes. True that, sister. It is. Now, is L a subset of O? If O is a subset of L, does that indirectly tell me that L is a subset of O? No. L has too many elements to be a subset of O. If your first set has more elements than your second set, can it ever be a subset of it? Like if this one has 10 elements and this one has 2, can this be a subset of that one? No, so we know that this first letter has to have at least the same amount of elements as this one, or less, right? Like if this one has 2, this one has to have at least 2, right? So that's not a true statement. Empty set. So the empty set is here. It's a 0 with a slash. It says empty set. So when people are like, what is this again? I'm like, formula sheet. Empty set. See? This is the only thing we have for this unit. These little pretty things. Okay? So the empty set is a set that contains no elements. Hence, empty set. So I think that was like, give me, like empty set, a set that's empty. No elements in set. Huh? Yeah. It's my type of definition. So the empty set is a subset of every set, which sounds stupid and weird, but it is. So like if I said, I'm here, the notation for the empty set is a 0 with a slash. For example, the set of all odd numbers in set E is empty because there are no odd numbers in set E. So provide another example of a set that's empty. You could say all the even numbers in set something, where is it? You could say all the even numbers in O, right? That would be empty because there are no even numbers in O. And then the complement of a set. The complement of set A is the set of all elements in the universal set that are not in set A. Complement is kind of like saying opposite. It's kind of like saying the opposite. The complement of set A is denoted by A prime. So it shows it right here too. A complement, right? You say the complement of A? Right here. So write the complement of set E. Complement of set E. So the complement of set E is what's not in E, but in the universal set, correct? What is in E? First off, E is 0, 2, 4, 6, and 8, isn't it? What is the universal set? 0, 2, universal set. 0 to 9, correct? 0 to 9 is the universal set, correct? So the complement of E is what's in the universal set but not in E. So what's in the universal set but not in E? 1, 3, 5, 7, 9. Okay. Then we're going to flip over. You guys are going to try this out. You're not going to do this workbook or anything, this assignment at all. This is what I want done for tomorrow, and we're going to go through it right at the beginning of class. So do this right now. That's it.